Once you know how to write the electron configuration of an element, you can draw a diagram that we call an atomic orbital diagram. The reason that this is helpful is because with an atomic orbital diagram, you can see not only where the electrons are, which sublevels they're in, but also how many are paired and unpaired. And then you can understand even whether that material will be magnetic or not. It's very cool. So when we draw atomic orbital diagrams, the important things to consider are the energy levels, the sublevels, and the orbitals. So in the diagrams, we generally draw a single orbital as a box. Now remember, an S sublevel will have just one orbital. A P sublevel will have 3 orbitals, and a D sublevel will have 5. F would have 7, but we won't cover those in this video. When you have an S sublevel in your diagram, you would need to draw just one orbital box. This is the orbital, and this is the sublevel. Let's try an example. Draw the atomic orbital diagram for the valence shell of arsenic. The first thing we need to know is the electron configuration of arsenic. So if you look at your periodic table, find arsenic here. We are in period 4, so I'm going to write it in noble gas configuration. So that means up until argon, it's exactly the same. So the electron configuration of arsenic, we'll start at the noble gas that comes before argon, and then we'll continue moving up. That brings us to here. This is the S block over here. So that means that we have 4s2 because both of those are full of electrons. And then we move through the D. Remember, the D fills after the S, even though it's a higher energy level. So this is the 3D sublevel, and it's completely full. Then when we move to the P block, we just have to put in as many electrons as it takes to get to arsenic. Now remember, in the P block, we're back to the normal energy level. So we're going to move back up to 4P, and we need 1, 2, 3 electrons to get to arsenic. So that's a quick review of writing the electron configuration. Now this question particularly is asking us to draw an orbital diagram of the valence shell. So first we need to determine what the valence shell is. Now a valence shell is anything in the highest N, so the highest energy level. In this case, the highest energy level is 4, because energy levels 1, 2, 3, and 4 all have electrons in them, and 4 would be the highest of that. And valence will also be any unfilled D and F sublevels. So if you have a D block that is not completely filled, those electrons will also count as valence. In this case, we do have a D, but it's completely full, so these won't count as valence. So our only valence electrons are in the 4s and the 4p. If you want to double check, that 2 electrons here and 3 electrons here is 5 valence electrons. When you look at your periodic table, because arsenic is in group 15, we would expect it to have 5 valence electrons, so we know we did that correctly. Now we've determined the valence shell, then we can draw the orbital diagram of the valence shell. So we'll need to include an S and a P. Remember, the S has 1 orbital for its subshell, and the P has 3 orbitals in its subshell. And then we can fill in the number of electrons. So 4s has 2, so we draw 1 pointing up and 1 pointing down. In order for them both to be in the same orbital, they have to be spinning opposite directions. So we represent the electrons as arrows pointing up or pointing down to represent their spins. If they're in the same box, they have to be spinning opposite directions. In the 4p, we see we have 3. So now we are going to put 3 electrons into these orbital diagrams. We have options about how we can put them in there. We could put them in like this, or we could put them in like this. Now remember, electrons are all negatively charged, so to put them in the same space creates repulsion. So it destabilizes the atom to put them in the same space, even if they're spinning in opposite directions. And so electrons will always fill up an empty orbital in a sublevel before going back to pair. So always fill up the entire sublevel before pairing electrons. So if I needed to add another electron, then I could go back and add it here, but first I want to fill it so that each one has 1 electron in it. In this case, we only need 3, so the 4p will have 1 electron in each orbital. So that is the atomic orbital diagram for the valence shell of arsenic. Now it's your turn. See if you can pause this video and draw an atomic orbital diagram for the valence shell of rhodium. First, you will need the electron configuration of rhodium. Krypton is the noble gas that comes directly before rhodium. After that, we're adding in some 5s electrons, and we're adding in 4d7 of those. Next, this is asking for the valence shell. If it were asking for the full atomic orbital diagram, you might want to consider writing out the entire electron configuration in its full notation. But this one's just asking for the valence shell, so that's why the noble gas configuration is helpful. We know that these are not going to be valence. After that, we want to see what is. So 5 will be our highest end, so these will be valence. Now remember, we also have to look for electrons in the D or F subshell that is not full. Since the D subshell can hold 10, but it's actually only got 7 in this case, this is not full, so this is also valence. So both of these will be included in our orbital diagram of the valence shell. Any S sublevel will only have 1 orbital. Any D sublevel will have 5 orbitals. If you forget how many orbitals each sublevel has, you can just look at the periodic table and count. Remember, this is the S block. The S block has 2 columns, and every orbital can hold 2 electrons, so it will only have 1 orbital. The P block has 6 columns, so that means it can have up to 6 electrons, which will fit into 3 orbitals. The D block has 10 columns, so that means that it will have 5 orbitals. And the F block has 14 columns, which means it will have 7 orbitals. All right, our S will have 2, and our D has 7. Remember, we're going to fill them one at a time. 2, 4, 5. Now that that's filled up, we'll go back and we'll pair any remaining electrons. So that's the orbital diagram of the valence shell of rhodium.